Hi and welcome to Unit 1 Topic 2 Video 8, and in this video we're going to start looking at Application 1 of vectors, displacement, velocity and acceleration. So learning goals, success criteria, have a pause, have a read. Now let's have a look at some stuff from last or previous lessons. So this is some stuff you may have covered already in methods, or certainly we've talked about briefly before. So let's begin with some kinematics. Now we have on one side our scalar quantities on the left there, distance and speed. Distance is how far you've travelled, speed is the rate of change of distance. So how far you travelled and how much time it took develops your speed. And acceleration is the rate of change of speed. On the right hand side we have displacement and velocity. Now displacement is also distance, but now direction is important. So these are now vector quantities. Displacement is a distance and a direction. And the big difference here is that if you change direction, it really has an effect on displacement, but distance is still pretty easy to work out. Displacement, for example, if I take 2 steps forward and 2 steps back, so I'm starting where I left off, where I left off, my displacement is 0. I've gone out 2 and back 2, so this motion out to here and then back to here, well, that will give me an overall 0 displacement, but it will give me a 4-step distance, or 4 meters, or whatever the units are. That's the difference between distance and displacement, because we don't care which way we're going for distance, but we do for displacement. And so then the resultant displacement is always how far you are from where you started. And the velocity is the rate of change of displacement. So in this example, the velocity technically is 0, but the speed is something else depending on time it took. So they're the important differences, and displacement is a vector quantity. So to summarize, displacement is the magnitude or the distance with direction. Velocity is the speed with direction. That's why when you're driving on the road, you will quote your speed, but you won't necessarily quote your velocity, because we don't care which direction we're traveling, we talk about speed. So we'll look at this a lot more in math methods, but for now, this is what you need to know. So just a quick summary of this. Displacement is a vector, distance is a scalar, velocity is a vector, speed is a scalar, and acceleration is kind of the naming word used for both. But to be honest, we're going to head in this direction for most of the maths that we cover, so probably we'll be using acceleration in that sense as well. Also, recall that speed equals distance over time, and so therefore velocity is equal to displacement over time. And acceleration is equal to velocity or speed, depending on which way we're coming from, over time. Okay, so let's have a look at an example and see where we go from there. So our example says a particle moves from 2,3 to 6,5 in 2 seconds, where the distance is measured in meters. So we've got seconds and meters, we're going to be working in meters per second. How far has it travelled? Well, let's have a look first of all at A, which is coordinate 2, 3, and B, which is coordinate 6, 5. And we want to know the distance that it's travelled in. Now this is a vector as well, but at the moment it's just asking how far. So we really are just looking for a distance. So hopefully you recall that that distance is fairly easy to calculate just based on Pythagoras' theorem for this triangle, or we could use the distance formula. So we have A, the distance will be equal to the square root of the difference in x, so that's 6 minus 2 squared, plus the difference in y, which is 5 minus 3 squared, and that's the square root of 4 squared plus 2 squared, which is equal to the square root of 20, or we could write that down as 2 root 5 in simplified form. And of course this is in meters. That's right. Now it asks for the speed. So remember, we're dealing with speed, and the speed doesn't have a direction. So our speed is just simply equal to distance over time, which in this case is equal to 2 root 5 over 2 seconds. So that's just root 5 meters per second. and that's our speed. And then we're after velocity. So this is where we really get to see the difference. Now, if we define vector AB, so AB here, well, that's got a direction because it's a defined vector. So we could actually define our velocity as this speed, √5, in the direction of AB. But we don't really know the direction of AB, so we're going to be a bit more specific. So remember, when we do polar form, which is what we're going to give our answer in, well, we do polar form in terms of an angle. Now, we'll also come back to Cartesian form, and I'll show you the differences and why velocity can actually be easy to work with sometimes. So let's start with our polar form by calculating this angle. And that angle will be, this was a difference of 2, this was 4. So we'll have theta is equal to tan inverse of 2 over 4, or a half. And that's equal to 26 degrees, 0.57. And so therefore, our velocity is equal to √5 is the magnitude of velocity, and 26.57 degrees is the polar angle, so the angle from the positive x-axis that represents the direction. Now, it's important to recognise as well that we have vector AB, which is a displacement vector. So this is, and I'll write this here, displacement, and it's equal to 2, my apologies, sorry, in terms of ij, it's equal to 4, 2. That's our displacement vector. So if we want to work out the velocity of AB, well, that's just equal to displacement over time. And so if we divide 4 by 2, we actually just get 2, 1. So our velocity is, for every second, we travel 2 across and 1 up. You can see it here, 2 across and 1 up takes us to there, that's 1 second. 2 across and 1 up takes us to there, that's 2 seconds. So we can define velocity as a Cartesian vector as well, or in INJ form is equally as good. And so I just need to remember to put down my little meters per second there, and we've got velocity defined in both ways. Okay, let's have a look at example 2. In example 2, a car moves from position A with OA equal to 2I plus 7J for 3 seconds with this velocity. Where does the car finish, and how fast is the car going? So fast means speed. But let's start by drawing what's happening here. So we've got a car, we've got O first of all, so I'll put O down here. And then we've got A, 2, 7. So this is 2, 7 as a coordinate. And so OA is this vector. And then we've got a velocity of 3, negative 1, or 3I minus j. So it's 3 across and 1 down. 3 across and 1 down. Now notice here I'm denoting what's happening each second. So, and we've got a 3-second movement. So the car starts here, moves each second in this direction according to that velocity 3I negative j. That's 1 second, 2 seconds, 3 seconds, and we'll call this is A. We'll call this point B, and that's where it ends up. So actually we can do this logically. We can work out where point B is just by adding that velocity on 3 times. But let's do this technically, mathematically. A, remember that velocity is equal to displacement over time. And so if I rearrange that, I get my displacement is equal to velocity times time, which is equal to, in this case, 3I minus j times 3 seconds, which is 9I minus 3j. That's the displacement in addition to, or from A. So therefore, point B is going to be equal to point A, well actually, OB, let's define as a vector. OB will define where B is. And it's equal to OA plus AB. Now, OA is where it starts, so that's 2I plus 7j. And AB is just the movement, so that is at 3 times 3I minus j, which we've already worked out is 9I minus 3j. 2I plus 9I is 11I. 7j minus 3j is 4j. So, and I should have little underlines here for all of those. But you can see that's our overall solution. So there's a logical approach to this, but if you know the mathematical way, when the questions get a bit more complex, which they will later on, you can deal with it mathematically and not have to build those diagrams on a logical understanding. And then question B, which I'll just pop up over here, how fast is the car going? Fast, in this case, implies speed, which means that we want to know what is the magnitude of the velocity. So that is the magnitude of the velocity, which is this, which is equal to the square root of 3 squared plus -1 squared, and that's just equal to the square root of 10. And again, what have I got here? 3 seconds, but I've got no displacement measure. So basically root 10 units per second. And that's the best we can do. So hopefully that makes sense, that we can build a bit of an understanding through a diagram, and we can develop it mathematically, and also how we get the speed from the velocity. All the best.